Okay, the tree diagrams, the difficult bits. Not too many of them. Let's take out everything that doesn't have tree diagrams in. Well, it's only that, okay? Let's tidy up. And let's look at the first two. The first 2 points here are talking about frequency trees. Some of you might not even know what a frequency tree is. Okay, here's a situation where you can use one. We've got a screening program that affects 1 in 1,000, and we've got a test which is 98% accurate. You test positive. How worried should you be? This is quite relevant to the current situation. Well, what you can do is you can draw a tree diagram. There are 100,000 people being tested. You can see that 100 of them will have the condition and 99,900 will not. Then you work out 98% of each of those numbers, and those are the ones which are correctly assessed. And then what you find out is that if you test positive, the chances you have the condition are less than 5%. That's actually quite easy to show with those numbers. It's a really counterintuitive result, though. Not many people would read those words and jump to that conclusion. Setting aside any relevance or otherwise of those particular calculations, the important point I want you to take away is this. Pupils find these a heck of a lot easier than probability trees because all they're having to do is count. Count, count, count. Everything we've done so far has been about counting. Finally, we get to the last 2 bits of our probability curriculum at GCSE. You're stuck with tree diagrams. And here is a classic tree diagrams problem. Bag containing 5 red beads and 3 blue beads. Make sure they know what beads are. At least I used the word beads. A lot of the books will refer to marbles. A significant number of pupils have not seen one. Okay, you take a bead out at random, put it to one side, take out another bead and draw a tree diagram. Okay, so here's how you start. There's my bag of beads. I take out my first bead. Obviously the probability of blue is 3/8, red is 5/8. I now have a different bag if I've taken out a blue one. And that bag if I've taken out a red one. So I now have 2 new starting points. I now work out what happens with the second bead. Well, if I'm on the top route and I'm down to 2 blues and 5 reds, I get those probabilities. And on the bottom bag, I get those probabilities. I then multiply everything together and get my final probabilities. Simple, isn't it? Only it's not. If you don't set them up for this right, they will get utterly confused, and I'll show you why. You see, look at those events there. Why are they multiplying probabilities? This is the first time they have ever multiplied probabilities. Up to now, they've added them because, well, mutually exclusive, although mostly they're just counting things up and working it all out as one go. But they can't add fractions. But multiplying probabilities, why do you multiply probabilities? Well, you can only multiply probabilities when the events are independent. That is the answer to the question. Work out the probability of this happens, state the conditions. I'm allowed to multiply because the events are independent. Okay, what do we mean by events being independent? I'm afraid the actual definition is really technical, and the arm-wavy definition that you'll have to use with your pupils can be confusing. I'll show you why. There is a Venn diagram. It's a version of the Year 10 options. Kids can choose music or choose Spanish. Are the events choose music and choose Spanish independent? Well, the answer is yes, because if you count them all up, the probability of choosing music and Spanish is 2/12 or 1/6. The probability of choosing music is 1/3. The probability of choosing Spanish is 1/2, and 1/3 times 1/2 is 1/6. Therefore, the probability of 2 things happening is equal to the 2 separate probabilities multiplied together. However, if I change that diagram just slightly, those events are not independent because the sum doesn't work. That is the definition of what independent events are. The way you're going to have to explain it is something like this. Events are independent if the probability of the second one is unaffected by the first. But tree diagrams are all about conditional probability, so the second one is affected by the first one. This is the magic of tree diagrams. The whole point of drawing tree diagrams for conditional probabilities is that they reconfigure the whole problem as a set of independent events. Look at this bag here. It's got 3 blues and 5 reds. This is an entirely different bag here with 2 blues and 5 reds. It has no memory of what happened to this one here. Therefore, this is a separate event. Therefore, you can multiply the probabilities. But it doesn't feel like a separate event, especially if you do it in front of the pupils, because they will see you using the same bag and taking out the same beads. so you can see the difficulty. You're going to have to figure out how to navigate your way through it. And of course, the last bit is, the question probably is, what is the probability they get two the same colour? Oh, that's easy. Multiply along the branches, add down the ends. Wait, what? You multiply along the branches because you can multiply probabilities when they are independent. You add at the end because you can add probabilities when the events are mutually exclusive. Now, I'm hoping by the time they get to this, they've got used to the idea of mutually exclusive. So they're only learning the independence rule, which is actually harder. This multiplication and addition rule are sometimes called the and or rule. I don't particularly like those words because in mathematics, the word or actually means and/or. So I think it's a slightly unhelpful bit of terminology. And that's about it for my thoughts on probability. Tree diagrams are hard. Leave them till the bitter end. Make sure they understand mutually exclusive events, outcomes, equally likely events, how to work out probabilities, and how to count stuff up before you touch them.